In the last two videos, we derived the Kolmogorov forward and backward equations. These two equations are actually deeply connected. One beautiful connection is that they are adjoints of each other. You can think of an adjoint operator as the infinite dimensional analog of a matrix transpose, except that the operators act on functions instead of vectors. In this video, we'll derive this relationship carefully, but first let's review the two equations. So the starting point of the two equations are stochastic differential equations. So xt is a stochastic process. The change of the process is given by a drift plus a fluctuation. For the Kolmogorov forward equation, this is also called the Fokker-Planck equation. It describes the evolution of the probability density function, given by this partial differential equation here. So we see that the partial derivative with respect to time is related to the first and the second order partial derivative with respect to position. So the backward equation describes the evolution of the expected value at future time. That is given by the function v. The backward equation is saying that the partial derivative with respect to t equals to something related to the first and second order partial derivative with respect to the position x. So the key idea is that we can write these equations more compactly. If we look at the forward equation here, we can use the operators. So we can think of operators are like a map from one function to another function. For example, the partial derivative with respect to time is an operator. It acts on the probability density function to give out another function. The forward PDE tells us it equals to the operator L star act on the probability density function. So for the L star, we can basically think of the terms in the forward equation as an operator, right? It involves the first and second partial derivative with a product with mu and sigma square. And the same for the backward equation. We can write this PDE in a more compact way using the operator L. So the key connections between the two equations is that the L and L star are adjoint operators. So the adjoint operators are like matrix transpose. But here we need to think of how matrix transpose works in the inner product. So suppose we have two vectors x and y. So let's say that the inner product between x and a times y, so that equals to x transpose ay. The idea is that if we just combine the x transpose with a, so we will have the a transpose x transpose y, and that equals to the inner product between a transpose x and y. So basically, in the context of the inner product, right, we can think of matrix as a map that can take one vector y as input and then output another vector. So if we want to move a to the first arguments to combine with x, we need to transpose it. And the same goes for functions. Now let's write this equation with functions. So let's say that we start with the inner product between function f and then L act on g. That equals to the adjoint operator of L star act on f, inner product with g. So the inner products of the two functions is defined as an integral. For example, f and g, the inner product is defined as an integral of fx times gx dx. So this resembles the vectors, right? When we have like a two vector x and y, the inner product is just the sum of I of xi and then yi, right? So for the functions, right, you can just think of the index becomes continuous. So it's like an infinite dimensional vector, right? We just replace I with this x in here, and then we just replace the sum with the integral. Then for the operator, in the case when the L is derivative operator, then the adjoint is connected with the integral by parts. So we'll see that in the derivation. Okay, let's get started. And for the starting point of these two equations, right, we always start with the transition rule. So let's use the transition rule of the iterative expectation that we use to derive the backward equation. So this is the equation we used to derive the backward equation last time. So the idea is that when we have a process from 0 to t, so this equation is saying that the average value at the time capital T, that can be broken down into two parts. We can find an intermediate time at small t, take the expectation, and that will still be random, so we need to take the expectation again. And in order to write this in terms of the integral, we can define the function v of t and x that equals to the conditional expectation conditioned on the x small t equals to x. Let me just copy the left-hand side. So we just basically break it down into transition probability, right? So on the outside, we'll have the probability of the time t at value y given the time 0 at starting position x0, right? So this describes the probability from x0 to an arbitrary value y, right? And then we'll have the another transition probability in the inner integral. So that's given by the transition at capital T with value x given time small t at y, we'll have v at capital T and x. Inner we'll have dx, and then integrate over dy, right? So basically the inner integral describes the transition from y to another value at x. And we see that this integral here is an expectation, right? This is just equals to the conditional expectation, so it's v, t, and y. Then this equation becomes the integral transition from 0x0 to t and y times v of t and x. Then we integrate, t and y, and then dy. If we look at this integral, it's a function of the intermediate time, small t. The small t simply breaks down the transition probability into two parts. And the important thing about this expectation is that it is constant over time. And by constant, what I mean is that regardless of where we pick the intermediate time small t, the iterative expectation formula doesn't care. It only cares about the start at time 0 and the end at time capital T. So it means that the time derivative of this integral equals to 0. For the simplicity, I'm not going to write the 0 and x0 anymore. So basically this time derivative equals to 0. So this is a key equation. And this must hold true for all function v. So the idea of the derivation is that the forward and the backward equation are connected through this equation. So basically using either function as a starting point, we can reach another one, right? We can use backward to derive forward or the reverse direction, right? So let's just start with the backward equation. So if we look at this equation here, right, we can just move the derivative operator inside and apply the product rule. So let me just change this operator into partial derivatives. And maybe let me just replace this variable with x as well to keep the notations consistent. Okay, so now we can just move the derivative operator inside. So we'll have the partial t act on the product between the function p and the function v. Then the product rule is saying that you have the partial t act on p, multiply that with the function v plus okay, so now if we look at this equation here, right? So we can actually use the backward equation to replace the time derivative of v. So basically the first term stays the same. Let me just copy it. From now, I'm not going to write the arguments anymore to just save us some space. And now we just replace that with the backward equation. That's going to give us and in order to reach the PDE, our final form will look like the integral of something times v equals to 0. And remember that this has to be true for all function v. So this will just imply whatever terms in here will equal to 0. So that's going to be a PDE. This is a goal. But the problem is that if we look at this, the second integral in here, right, we have the partial derivative act on v. So the idea is that we can use integral by parts to make this integral into v times something with respect to the derivative of p. So let me show you that. Okay, so so let me just grab this integral and separate out the terms. So we'll have the integral of minus p times mu times partial v partial x dx minus a half the integral of p times sigma square, the second derivative, the integral by parts formula is saying that when you have an integral of u times partial v partial x dx, that equals to so that equals to u times v minus, let's say that the bound goes from negative infinity to positive infinity, right? then that minus v times the partial u partial x dx. Then we can just basically apply this integral by parts formula to our integral. So we'll have minus p times mu times v from negative infinity to positive infinity plus the integral of v times partial p times mu partial x dx. For the second integral, we may need to apply it twice. Okay, let's just do the two terms separately, because for the second integral, we may need to do it twice. So let me just label this a little bit. The idea is that this first term goes to 0 because we're going to assume the probability density function vanish at the negative infinity and positive infinity. Okay, now let's look at the second one. And for the second one, we'll have minus half times p sigma square times v partial x plus a half. Then we'll have the first derivative of pi times sigma square partial x times the partial v partial x dx. And again, this term goes to 0 for the same reason. And then we're just going to apply the integral by part one more time. So that will be a half times partial x act on p times sigma square times v and then have minus a half so the second partial derivative act on p and sigma square times v. And here, once again, we're going to say the derivative of p, the first order derivative also goes to 0 at the boundary. The probability density vanish really fast at infinity. And then, when you multiply that with some other things, that still decays very fast. So these terms will vanish. Okay, good. Now we are in very good shape, right? Because we have removed the dependency of v with derivatives. Okay, now we can just bring everything together. So we'll have partial t act on p times v plus, we're just going to copy these equations, partial x act on p times mu times v minus a half partial x square of p times sigma square times v Now remember, this function has to hold true for all function v. So it just means that we have the partial t So it just means that this term must equal to 0. This is the only way we can make this integral equals to 0 for all function v. And that is exactly the Kolmogorov forward equation, the Fokker-Planck equation. Okay, good. Now we see that the forward and the backward equations are connected through this identity right here. Note of the algebra that we just did, it just integral by parts. So structurally, this entire derivation is very elegant. So let me just show you that. Okay, so I'm just going to translate this derivation into a very compact notations with inner product. Okay, so I'm just going to write it on this side here. And then we're just going to rewrite the integral into the inner product. So for the starting point, we have the partial t act on the inner product between p and v that equals to 0. I should denote this inner product is with respect to x. And then we can just apply the product rule. It's just going to give us the inner product of partial t act on p plus partial t act on v that equals to 0. And then we can use the Kolmogorov backward equation to replace the second one with the inner product between p and l act on v. And we'll copy the first term. And then we can use the adjoint operator on the second term. So that will become L star act on P, inner product with V. And then we'll copy the first term. Okay, I think this L operator has a minus sign in here. Yeah. Okay, yeah, so now we can just combine the terms. So we'll have the partial t act on p minus L star act on p inner product with v equals to 0. And because this inner product is true for all function v, so it just means that the first argument must be 0. So you have the partial t act on p minus L star on p equals to 0. And that is the Kolmogorov forward equation. So we basically apply the backward equation in this step. And we see that these two equations are connected with this identity. So all the algebra that we just did, it just integral by parts. So when we have like an explicit form for the L operator, we need to integrate by parts to find the L star operator. We'll see that structurally, this is very elegant. This is all we need to see the connection between the forward and the backward equation. Okay, so that's pretty much about this video. We connect the forward and backward equations through the adjoint operators. Basically, underneath both equations is the same object, the transition probability of the stochastic process. So in the next video, we'll look at a very cool idea called the path integral. So instead of looking at the stochastic process with differential equations, we'll look at the space of the paths themselves, where the expectation can be thought of as summing over all the possible paths the process can take.